Hello and welcome to one more discussion with Professor Sukumar. Professor Sukumar is a well-known scientist working in the area of drug discovery, computational biology. He was originally a quantum chemistry researcher, educated in US, worked in US, Germany, India. Um, Both of us share a passion for drug discovery that has gotten a collaboration of sorts going. Also, he published a terrific book on drug discovery. The reason we have published more than 4,000 books with IonCure, but this one is really, really special. I've come to meet him at his home to take the interview in Himachal. We are actually sitting in his balcony, and you can hear, bird sounds, insect sounds, and background ambience you can see of apple trees and other trees. It's absolutely beautiful here. The reason I've come and why I really love this book a lot is it is looking at change, and it's not a minor change, it's a revolution in the field of drug discovery. Drug discovery, pharma are a multi trillion dollar enterprise. They are vital for human survival, the medicines, and they are being completely changed now with the advent of AI and computational approaches, whether it's computational biology and computational chemistry. It's an honor to have Professor Sukumar, and what I'll ask him is to summarize the role of AI, computational biology, and computational chemistry, computation in general in drug discovery.
So there are uh, there are several aspects of the computational drug discovery, of what is broadly known as computational drug discovery. They can broadly be classified into structure-based and ligand-based. So in the ideal case, you know what is it in the body, the, the, the target organ and the enzyme or protein that is causing the disease. And you want some drug which will bind to that. So if you do know that, and if you know the structure of that enzyme or that protein in atomic detail, then you can do what's known as structure-based drug design, where you can say, okay, what is the region of the molecule of the protein where where we need to target, what kind of molecule, drug-like molecule, will fit into that target, so computationally you model the interactions, model the intermolecular interactions in order to find a useful drug. But in many cases, you don't know what is the protein. In many cases, you don't know the structure of the protein, because many of the proteins are membrane-bound proteins, which have been traditionally very difficult to crystallize and find the structure. Now, of course, things are changing with cryo EM, but it's still, there are a large number of proteins for which we do not know the structure in sufficient detail to be able to look at all the interactions, to be able to compute all the interactions. So then what do we do? Well, if we know some drugs which happen to work, and we have thousands of years of human history. We have different medicinal systems, where people have experimentally discovered various formulations which work. And we want some formulation which works in a similar way, or which maybe does better, is more potent, works in smaller doses, works faster, has less side effects. And so these are then investigated using ligand-based drug discovery. And here's where AI comes in, where we use pattern recognition techniques, artificial intelligence, in order to learn the data about the drug-like molecules, and see what is it that is common to these drug-like molecules that is not there to some, the non-drug molecules, and thereby we learn what is, or rather and nowadays, it's the models themselves are training themselves, teaching themselves in order to discover what are the interactions, what are the features of the molecules. So there are chemists have over the years developed several molecular descriptors which quantify certain features, certain aspects of the molecules. They have developed certain techniques, certain combinations of features, they're called pharmacophores, which you have a combination of these features uh, which enables the molecule to act as a good drug. And therefore, you look for uh, other molecules which have this combination of features. And combination of features could be like certain atoms, certain kinds of atoms, and certain range of distance between those atoms, so that molecule will be able to bind to the drug, even though you don't know the structure of the drug at this point. So, and nowadays, what we are having, we have AI techniques like language models, which are just learning from the molecular formula. There's something about the interaction, something about the similarities between the molecules. So, these similarities between the various possible drug molecules are encoded into what the computer scientists call embeddings. And these are then the the computer then generates new molecules which nobody has synthesized as yet, just which have these combination of features which might uh, give them drug-like properties.
Absolutely. And there is obviously interesting things happening with natural language processing that you can evaluate a lot of literature,
Yes.
which for humans will take forever. Then you have a structure which is being predicted with such high accuracy that even if you don't have structures like with AlphaFold,
Yeah.
AlphaFold, in my opinion, was a bigger achievement than putting man on the moon, right? Because you can predict things from sequence, and then you can dock, and you can understand what will happen. Like earlier, we used to do in my academic job in drug discovery. One of the things they wanted me to do is just look for third channel toxicity. Very silly thing because there is so many other targets of toxicity. I understand the historic reason for third channel being an important one. But now you can put in not one or two, you can say, okay, these are all potentially responsible for toxicity. Let us now virtually screen, let's say, all these 1,000 molecules in less than few seconds for all these potential targets. What would otherwise be 50 researchers' lifetime of research? So it's saving money a lot. So,
Yeah,
I mean,
not just 1,000. The software which I have developed can screen 500,000 molecules, half a million molecules in half an hour or something like that, right?
yeah,
So yeah, and this is just using a single processor. So give it more computational power, you can screen billions of molecules. But that's still nowhere close to the number of possible molecules, the number of possible molecules that could have, drug-like properties.
so yeah,
That's
that's
something like 10 to the 10 followed by 60 zeros.
yeah,
That many. If more, there are more possibilities for molecules than there are um stars in the entire universe.
yeah.
So
Will not run out of business. So just
yeah,
hope that longevity tax gives us 200-300 years to live, and we can convert that into a lot of money by generating a lot of molecules. Sorry, ending it on a lighter
okay.
note, but I am a fan of longevity tech, not just being very light about it. Thank you for the great question.
Thank you.